So now we're going to do some Jamboard practice problems. I chose particularly the toughest ones to do with you guys. And the first one that we're going to do is number 4, looking at carbon dioxide, CO2. Just as a recap, here's the steps that we're going to take in order to draw the Lewis structure for carbon dioxide. The first thing that we want to do is count the total number of valence electrons. So in order to do that, let's look at each of the elements we have in our molecule. We have carbon, which is in group, why can I never remember this? Carbon's in group 14, so it has 4 valence electrons. Oxygen is in group 16, so it has 6. The 2 here tells us that we have 2 oxygens, so we need to multiply this by 2, and we get 12. Okay. So that means in total, the number of valence electrons that we're dealing with is 16. All right. VE stands for valence electrons. 16 valence electrons. Now I'm going to erase this just because I need to have space to draw my stuff. But we're going to remember that. 16 valence electrons. All right. Step number 2, decide who is the central atom in our molecule. And remember, central atoms are typically the ones that are like only one of its kind out of your molecule. So in carbon dioxide, because there's only one carbon, carbon's going to be our central atom. Oxygen, we're going to distribute around carbon. Just because I have experience with this, I'm going to put an oxygen here and an oxygen here. I know you guys may not know all this kind of stuff, right? So if you put oxygen down here and oxygen there, that's fine. You're going to get the same answer. It's okay. Okay, central atom, other atom, that's good. Step number 3, draw in single bonds to connect everybody. So simple as that. Now, what do those single bonds represent? Remember, one single bond is 2 electrons. So there's 4 electrons that we've taken care of. We have 16 total that we're dealing with. Here's 4 of them. Now we need to go back and distribute the remaining valence electrons amongst the atoms. So we have 12 that we need to take care of. We're going to start with our oxygens, start with the outer elements first. So I'm going to put 2, 4, 6. Okay. Now I'm going to go to the other oxygen, and I'm going to put 2, 4, and 6. So just double check. Did we actually account for all 16 valence electrons? We've got 2, 4, 6, 8, 10, 12, 14, 16. All of our valence electrons are accounted for in our molecule so far. But now we need to go and double check, do the atoms actually have an octet? So if we start on this side, let me use my paper here, and I kind of like cover these guys up. Does this oxygen have an octet? Well, it's got 2, 4, 6, 8 electrons. So that oxygen is happy. If I go to this oxygen, notice its mirror image, so it's good. This oxygen has an octet. But let's take a look at carbon in the middle. Carbon by itself here, it's got 2, 4. So it's not stable yet, it's not happy yet. It needs 4 more valence electrons. So how are we going to make that work? Step number 5 says form double bonds when you have an atom that doesn't have an octet yet. What that means is between oxygen and carbon, we want to turn this into a double bond, which means oxygen is going to share one of its pairs of electrons with carbon. Now that's cool. That's like a good thing, right? Because if we share, oxygen gets to have these 2 electrons, carbon gets to have these 2 electrons, and carbon is one step closer to having an octet. So the way we draw that is we erase this, what we call a lone pair here. We erase that and we draw another line between oxygen and carbon. If we go back and we double check octets, this oxygen here now has 2, 4, 6, 8. That did not change, right? Oxygen is still happy. Carbon now has 2, 4, 6. Closer, but no cigar for carbon quite yet. Now, there's multiple ways that we can solve that problem of helping carbon get to a full octet, and this is what college chemistry is gonna like really push on you guys. We're just gonna do it one way, and we're just gonna leave it at that, all right? Carbon needs 2 more valence electrons. It could share with this oxygen again and form a triple bond. It could. The way that I've always learned it, that it's like the better way to do it, is that carbon's gonna form another double bond over here with this oxygen. So these 2 valence electrons are now shared between carbon and oxygen. If we double check 2, 4, 6, 8, this oxygen is okay. This carbon now has 2, 4, 6, 8, carbon is okay. This oxygen we already know is okay. Everybody's happy, everyone's stable, everyone has an octet. They're just sharing a buttload of electrons. If you think back, do we still have all 16 valence electrons accounted for? 2, 4, 6, 8, who do we appreciate? At least once that had to happen, come on. 10, 12, 14, 16, everything's good. All right. Woo! Carbon dioxide. What a crazy molecule. Aren't you glad that we did that one together and you didn't have to do it on your own? All right, so there's carbon dioxide. Like I said, it's a tricky one. In college, you'll see it all the time if you take chemistry classes. Okay, the next problem I'm gonna do is number 5, BF3. All right, so we've got boron, we've got fluorine. In fact, we've got 3 fluorines in this molecule. Step number 1 says we want to find the total number of valence electrons. So if we look at boron, boron is in group 13, so that means we're going to have 3 valence electrons. Fluorine is in group 17, which means we have 7 valence electrons per fluorine atom. The 3 tells us that we have 3 of them though. So that means for fluorine, we have 21 valence electrons. But in total, if we add them all together, 21 plus 3 means we have 24 valence electrons. Okay. Who is our central atom going to be? Again, think who's the loner in this group. There's only 1 boron. Boron is going to be our central atom. Right, boron first. Then we want to put fluorines around it. Specifically, we want 3 of them. Okie dokie. Next step, draw in single bonds to connect everyone. Doot, doot, doot. All right. Then we're going to take care of the rest of the valence electrons that we didn't already account for. So far, we have 2, 4, 6. We need to add 18 more electrons in there. So fluorine gets 6 of them. This fluorine gets 6 of them. This fluorine gets 6 of them. So we think to ourselves, all right, did we take care of all of our valence electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Okay, it's good. And then we check our octets. So fluorine, 2, 4, 6, 8. This fluorine, same deal. This fluorine, same deal. And then we look at boron. And welcome to chemistry, the world where things make sense, but then they don't. Boron is one of, I think, 2 elements that is happy with only 6 valence electrons. I think it's boron and aluminum are like one of the 2 elements, are the 2 elements that are just happy without having 8 valence electrons. So, and we're done. This is it for this problem. All right. Now, if you ask me to explain it, that's higher level chemistry that I want to get into. All you need to know is that boron is happy with 6. All right. So there, that's that one. That's all we have to do. So that was number 5. Let's carry on into number 6. And number 6 is kind of related to a lot of biology stuff, actually. Whew! All right. Number 6, the problem originally says, Okay, I'm going to pause this video. I think my video froze. You can probably hear me. You just can't see me. I'm going to pause this video. I'm going to start another one.